Yeah, hello everyone. Thank you, Jerry. This talk is about QED.jl, our ecosystem. First of all, wait, is it the Zoom sees us here? Okay. Yeah. Okay. First of all, I just want to motivate our physics case, just to show you what kind of things we do and why it's a bit different to the standard stuff done at the LHC or something like this. So we are part actually of a bigger experimental collaboration called HiBEF, and this does experimental stuff at the European XFAL, which is a big ass laser at DAISY, like 3 kilometers long. And this laser produces high quality X-ray laser beams. What means laser beam means it's coherent, huge photon density and high frequencies. For us, it means 10 keV and above photon energy, which is, I don't know, not that much, but if you have 10 to the 20 per square per cubic micrometer, it's like a lot of things which is going on there. And we, in this experiment, among other things, we want to collide this big as laser beam with some scattering particles like electrons and photons, and want to investigate some phenomena like multi-photon scattering due to the high coherence, non-perturbative effects due to just this intermediate regime between classical and quantum field theory, then unstable vacuum effects, what you usually don't have when you have just standard energy fields, is that electron proton pairs just pop out of the vacuum, and due to the presence of the field, they become real. So they took part of any scattering process which might happen in there. And then you can have something like what we call electromagnetic cascades, which is similar to the things you see in a detector at LHC, but here from vacuum, driven by the laser. This is the different part. And I mean, you might ask, why is this important? I mean, QED is known for decades. But these extreme situations where you have high intensity and high energy and a huge amount of coherence, you found these things, these properties, you found them in nature. For instance, near a certain type of stars called magnetars, which produce really intense magnetic fields, which then interacts with the surrounding nebula around these neutron stars. And this light, which is emitted by this interaction, is then be seen at a telescope. And what you want to understand how to trace back to the actual magnetosphere of such a star, because this is really unknown. But also high luminosity electron-positron colliders, because due to the high luminosity, so you pack a lot of particles in a bunch on a certain volume, in the interaction of these particles, they feel the fields of each other. And so you need to take into account the fields when you calculate the hard scattering process. And this is not done yet, but the theory I will present you today might help to understand this. But also from a completely different angle, there are applications in material physics where there are materials which are, where the lattice of this material, when this metal is built in a way that there are quasi-particles in there which act like fermions in a really, really strong electromagnetic field. Strong means high intensity in this case. These situations with high intensity fields you find also in these regimes where, or in these regimes where you don't think that they're in there. And in the end, my field directly at HiBEF is the relativistic plasma physics. So you have a highly ionized gas, and you shoot with an X-ray laser on it, and you want to understand how the laser looks afterwards, so you can do imaging and probing. Okay, I hope this motivates a bit while we are doing these things. And the thing is, usually you do these kind of experiments with optical lasers, so lasers with EV frequency, and there the physics is completely different. So you have it's like going a train going through the thing, because everything interacts collectively. So you don't have this particle picture anymore. However, if you go to an X-ray laser, so you have higher frequencies, the laser starts to become particle-like again. And this is what we figured out now. We see this in the detectors, that it interacts not the collective interaction with a field, but it interacts single photons, but a lot of them and with a lot of properties. And therefore, what we proposed was okay, let's particle physics beam with the electrons. There's a particle physics like laser thing. We collide this. Why we don't use like particle physics like simulation tools for this? Like a natural way to go. I mean, the community where I'm from does not know these things, so I need to introduce that. And just to show you how it looks like for us, it's like the upper branch is like the theory branch where we design like some compute models like QED or extensions of it. Then we calculate differential cross sections. All of you know this. Then you do Monte Carlo event generation with the cross sections. Also fine. Then you can do quick dirty, or you can put these events into some like showering clustering codes, or in transport codes, or in detector simulations, whole experimental simulations, and so on. And in the lower branch, this is like the experiments work, similar to something like AHC. You have a machine, things collide, you transport signals, you amplify signals, and eventually you detect them. And what you want to have in the end is like standard event reconstruction and analysis, what you know maybe better than me. Okay, and just to give you like a quick glimpse of how theory looks like for us, this quantum field theory. Usually it's something like QED, like the vertex here on the left-hand side. One of you knows. But for us, there's a laser field, which means that it has like an energy spectrum. It has temporal structure. It has like field properties. And we include these field properties by a so-called background field, but it doesn't matter what it is. It just means for us it's now here that we blow up the vertex. And this vertex contains now like a lot of factors and whatever, but the important part are these phase integrals. And these phase integrals like consuming all the properties of the laser field, which means that the vertex is not just like a point interaction anymore, but an interaction with like a regime, an energy regime in the end. And most importantly, if you interact with the laser changes. That means these phase integrals change. And then you need a mechanism to actually update these fields and calculate the process again with the updated field. That's why we call it like dynamic Feynman rules, dynamically generated Feynman rules, because they are adopted to the actual physical situation. And this also means we can't use for anything of this, we can't use established tools from high energy physics because they don't do this. This is the important part. That's why we start something new. From here, we just do the standard differential cross-section stuff. So we draw some Feynman diagrams. We use some tools to generate a matrix element. We put this in our golden rule, and we calculate differential cross-section. Every one of you knows it. I mean, for strong field QED or laser physics, it's a bit different. I mean, the structure is the same, but for instance, the incident flux is a bit different because it involves a laser. The squared matrix element is different due to the different Feynman rules, and the phase space measure is a bit different because you have a sort of interaction between the background field and the process itself, which makes energy momentum conservation a bit different. Here I just wrote down like the standard energy momentum conservation and the cuts like in standard quantum electrodynamics, but usually this function big H is a bit more complicated. Just the like boundaries in your phase space due to experimental situation. Okay. And then in the end, we do event generation. I don't want to go too much into detail with that, but what we need is a total cross-section. To get a total cross-section, we integrate over the differential cross-section. Since the differential cross-section is a multi-dimensional or function on a multi-dimensional space, we use Monte Carlo integration for this. To make this more efficient, we use important sampling, which is this proposal distribution G, or PDF of the proposal distribution, where we draw our samples from, and then we just like calculate this sum. However, what we want to have is events in the end, and when we call like this thing here, like the weight of an event U, then this weight is follows the differential cross-section. It means it's not one, and nature doesn't care about differential cross-sections, so we need to unweight. So we need to find a transformation from weighted events to unweighted events. And for this, we usually use the rejection method. So we just normalize our differential cross-section. So the maximum is 1. And then we can say, okay, we draw a sample, a weighted sample, and we keep the sample with a probability, which is given by the normalized differential cross-section. So it's just a standard method. And it works, it's really robust, so that's why we use it. Problem is, I mean, for this one-dimensional case, it's somewhat easy, but when you have higher dimensional cases, this becomes really, really inefficient. That's why we need to find like good proposals, like good functions G, to do the important sampling quite well. And here on the left-hand side, you see like an adaptive grid from Vegas, which does this kind of approximation of G of U. Okay, coming to QED.jl. So this was just concepts, so things we use to actually formulate our stuff. And now we wrote a software about it. So because, as I told you, most of the things out there we can't use. And first of all, the thing was, it is a bit of involvement finding out what kind of structures you want to have. And the first thing what we did is like essentially doing, okay, what kind of things we want to have. So what is our dream state want to have? And then this usual thing, it needs to be open source, needs to be user-friendly, modularized, extensible, generic enough so that you can just put in things. I mean, something like Julia's linear algebra, but for this would be nice. It needs to be performant because we want to generate like millions of events, like and don't want to wait like a month for it. And best case would be it runs on CPU and GPU without any big tweaks and so on. And we came up with something like this. I don't want to go into detail with all of this because some of you might seen this picture in another talk I gave. I just want to go a bit more into detail with the dark blue parts. I mean, most of these things are just concepts how we want to arrange interfaces, what like kind of algorithms we want to have in there, and so on and so on. A lot of these things are not built yet. However, these blue parts we decided to this dark blue parts being part of our proof of concept. So just that we find like a sort of program where we can show that it works. And I want to go a bit more into detail with these blue boxes now, but just to like remind you, this whole concept thing is actually not restricted to QED. So it's like standard stuff from particle physics, but we like put our specialized implementations for QED in there. But you can actually do everything with it. So you can also like QCD and weak interaction. You could, in principle, implement this as well. But we are just a small team, so we need to focus a bit. Okay, starting with QED base. So it's like a small package where we define Lorentz vectors here based on static arrays.jl. Also like spinors and direct matrices. We also plan doing like helicity amplitudes. So these are like just the standard stuff. The last point is a bit more important. We actually find like a type hierarchy for particles, but only as like labels for particles, which you can use for dispatch. Similar to what corpuscles.jl does, but we do it like in a type hierarchy to say, okay, the propagator of a fermion, and then we need like a fermion point in our type hierarchy. So that's why we use this one, and we define all sorts of properties like masses and charges and lepton number and what you want to have, just as an interface for the particles. That's it. And we also define like base states, like this U of pi, you maybe know. This we can also like just define with an interface. Okay, but also like maybe a bit boring for you, it's like QED fields. It's like the electromagnetic fields and all the laser stuff. I mean, the base type is just an abstract field. We define some sort of properties in there, which you can then use to more or less by default implement a lot of stuff. So for instance, you have a domain, you have a reference measurement and amplitude for a general field, or more specialized version for the pulse plane wave fields. You have like a phase duration, how wide the pulse is. You have like a phase shape, the envelope, we call it as a function. And then you can just generically implement amplitudes, Fourier transforms, phase integrals, whatever you want. And we just like dump in some third-party libraries to actually calculate, for instance, the Fourier transform of a given pulse. It's just organization in this case. Okay, then we I come to something which is maybe a bit more important. This is QED processes, where we model all the things which happens with which we need for differential cross sections. So, and here this is like more or less the default way to call a differential cross section in our library. It's like a function differential cross section, and it has 4 arguments. It's like a process, a model, in phase space and out phase space. And I want to go a bit more into detail what these different things are, because in every of these arguments, or behind every of these arguments, is an interface. So that means, for instance, here, this is the scattering process. We have an abstract scattering process type, which is just a label for a generic process. For instance, when you have like the Compton process, which is usually just electron photon into electron photon, but this initial photon could be like a photon light, like a laser. it's also like a photon-like in our case. And we use this just for dispatch because then it's like really, really easy to like plug and play with these things. And then we define an interface for it, and then you can just call it like in this small code snippet here. One like a bit odd aspect is we use spins as well in dispatch. So we have types for spins and polarizations, and here are types in with called all spin and all polarization. These are just like types we use when we want to like sum up or average over spins and polarizations. And this means that this process here acts like two processes, one of, or in this case, 4 processes for any combination. That means when I calculate matrix elements and all these things with it, if something is spin dependent, it just does not only calculate like the matrix element for this one spin configuration, but for all of them. So this is like, comes really in handy if you want to have like just summing up things because you never need to write down something like 4 combination of spins, do this. You never need to do this. Then we have the model. It's like the abstract physical model. It's like just also with an interface, which is the same for the models as for the process. It's just a label where we can configure the compute model which is used. For instance, we use perturbative QED for Compton, then we get something like Nishina. Or if we use perturbative QED on something else, we get the perturbative QED for it. But we can also use like a Gaussian field as a profile for the laser pulse, put it into a model and calculate Compton with this, so it is Compton in a laser field. So this is like, comes really in handy if you want to do these plug and play things. And also like one point I want to make here is all of these steps calculating the differential cross section, so having the matrix element, having it squared and averaged, having the phase space factor, the incident flux, and so on, you can dispatch on all of them. This is a really important part because when you have something like Compton where you sum up over all spins and polarizations, there's an analytical formula for this. So you can just plug this in to squeeze out performance. So this type of interface here allows like arbitrary optimizations because you can, and for all instances, if you have something you can calculate analytically, you can just dump it in. So this is the easy part. And then in the end, in and out phase space, currently just look at them as like a sort of abstract vector, abstract matrix where the elements are full momenta. I mean, what we actually also need is kind of coordinate systems and frame of references. They are somewhat hidden in there. And currently we construct this. This is why I don't want to show more of this. But in the end, it's something like this. It's like an abstract vector. And vector in this case means this is one phase space point. Because remember, we have several particles in the out phase space, which means like phase space is described by, I don't know, 4 or 5 full momentum in the end. And a matrix if you have a collection of phase space points. Good. Can we do this afterwards? Can you? Okay then, because I have some slides left and I don't want to go that much over time. So, yeah, and here for processes, just like everything together. Like you define a process, you define a model, you define an in-phase space here on the coordinate base, which internally translates to the full momenta, just with a default like default coordinate system and default frame of reference. You define the cosine theta of the scattered photon. You define the azimuth angle of the scattered photon. You collect batches a bit, like combining all the points there, and then just calculating like in a vectorized way. Sorry, the vectorized way, the differential cross section. And the physics here does not matter. It's just like to show you like the interface works. And another point is when I now say, okay, this is like all combinations. I mean, this here is just klein China. And when I now say, okay, my incoming photon has a polarization in X direction, then again, just use pol X here. This is the small part which changes, and I got a completely different branch in the calculation. And our goal is to do this for all the things we can combine. And currently it looks good. Yes. Just a small interlude, also like a concept we discussed a lot in our development of the thing was how to deal with functions we want to just calculate on things, getting out a number. So you have a function f, you have an input vector of which you want to run over, like phase space points or something like this, and want to calculate the differential cross section. And you have parameters which parameterize your thing, which got fixed before the calculation. So you have like the kind of setup, and then you have a calculation or computation phase. And then you want to collect everything, wrap everything up. And for this, we have like an abstract compute setup where we put in like, or we define like a sort of quantity you want to calculate. You have an assert valid input where you just look if the input vector is correct, like from shape and so on. Then you have the computation itself, and then you have the post-processing. And this structure comes really in handy if you want to like generalize the input of a certain thing like a sampler, because then you can base it on a setup, and it does not matter what a setup is, because it knows it has a compute function, it knows it has a validation, and you can use the post-processing to wrap things up. And the fun part about this, you can have for this type of calculation, just evaluation of a function, you can implement like a real compute function with just all of this, like in sequence. You can implement this, for instance, for different types of vectors, like the standard Julia vector, but also Q arrays and ROC arrays and so on, because you can overload the compute function. The only thing you need here is like a generic version of underscore compute, and then you can do all these things. And this is like, we don't have implemented all of these. It's just like our dream state to have these, and we currently investigate to implement it also for like for the Q arrays and so on. Okay, last but not least, QED events. So this is our event generator, which we implemented now. It's based on also on base type abstract sampler. I know the word is maybe not that nice. Maybe we change it at some point. And for this, the interface is quite easy. Like you have an element type for the things you want to produce. You have a setup, the thing I showed you the slide before. You have a weight where you can just ask what is the weight of this sample. And you have overloaded distributions underscore rand. Bang. And the reason currently we bound to the distributions.jl because they have a lot of utility functions in there you can use. They have a lot of implementations of rand and rand bang, which you can directly use out of the box. Currently, we do this till we see limitations. And when we see limitation, we do our own thing. But we want to stick with the function name rand, because everyone knows random numbers are generated rand, so we want to overload this definitely. And then we have the rejection sampler thing I told you, where like in addition to all of these other interface functions, we have a proposal distribution, which is by itself a sampler. So it's a rejection sampler is a sampler which contains a sampler for the proposal. It's quite easy, straightforward. And then you can, with this kind of constructor, you can like have different forms of proposal samplers. For instance, currently we have implemented uniform Vegas and NIS. This is the neural important sampler. Tom will say something more about this. MCMC currently under investigation. If we can use it, how we can use it, if it's nice or not. We also look at BAT a bit, or BAT.jl a bit about this. We need to see if we can use this. But the good part is we have also like a specialization of every sampler called process samplers, because sometimes for a given process, there is known the best sampler. There's just an analytic inversion sampler, for instance. And there you can just like also implement like all of obscure samplers you want to have, like, I mean, Kahn and Koplinger for Compton is like known, but there are also like these obscure one, like it's Mutlu, which is like a sampler from the 70s, or the Bright Wheeler sampler for pair production from Keck, for instance, or a custom field sampler for our case, where we draw numbers from the field itself and then use this to draw numbers from the process. So you can actually like specialize here, like directly on the process you want to have. So you have two angles: the process you want to have and the proposal for the rejection sampler, which you can like play with to see what is the most optimal way to sample your process. Okay. How much time I have left? Okay. It's just 2 slides. So, okay, then everything together, just for Compton again, because I don't want to bore you with physics. Here we define again just the process. We define our model, but with QED, we define an phase space, which is essentially like the energy of the incoming photon, which is here 500, that's the electron mass. Then we define our setup, which we call differential cross-section, because this is what it is. And remember, we can just compute the differential cross-section by call compute on this type with the final phase space. And then we define a sampler, which is by default with a uniform rejection sampler with a uniform proposal. And then we just call the round function on the sampler. That's it. And then it produces samples. Here, in this case, like 1 million samples, then have like wrapped up a bit of plotting in a plot combine function, which plots me these three plots here. On the left-hand side, you see like just the 2D histogram of what comes out. Then you have like a projection on the cosine theta axis in the middle, which just shows a green. I don't know if you can see this, but the line from the differential cross section is like laying exactly on the process itself. And then on the right-hand side, you see like for the rejection sampler, just a histogram of weights. And here you see, because it would be nice if they are near to 1, so you don't reject that much. But here you see that like 80% of the proposals were rejected, but only like approximately 20% will get accepted. It's not that efficient, at least not. Huh?
It's not the worst I've seen.
Yes, but I think the things you have seen have are really high dimensional. This is just 2-dimensional. I need to say it's a 2-dimensional process, so it should be better. Here the same thing, but using Vegas as a proposal. Again, okay, the sample is the same. Nice, but the weight distribution is way better. So you have like an acceptance rate of 80% around about, and I mean, which means only 20% get rejected. And this is actually just to show you, okay, we can plug together these things. We are not finished yet. Most of the things you have seen here are on the prototype stage. It works, but it is like covered under a lot of like try and error, which you currently have. But we are now like on a good way to put everything on GitHub, put everything like clean it up and publish it in a way of a release. And with this, instead of a summary, just give some lessons learned doing these kind of things completely from scratch. So we had nothing in Julia for this particular case. First of all, from the theory side, there's something beside a standard model, which is standard model, but not actually a standard model. Dynamical Feynman rules are really hard. It's really hard to do these things. Then for QED.jl, easy interfaces are really hard to design. To figure out what kind of interface you want to have for all these things. I mean, this looks, some of these parts look really trivial. You need like this and that and that and that. But if you just write it down and try it with something, you figure out, oh, I need this information at this point. How I get this, where I put these things. So it's really hard, even if the interface looks really easy afterwards. Then orthogonal design is mandatory. If you want to have a student working on something in Julia, it is really nice to have orthogonal models where you can independently work on things, just agreeing on the interfaces. This is really nice. And Julia is a friend. Julia does really good job, helps you really a lot with these things. And for the event generation itself, good proposals beat bad proposals. This is nice. Good implementations beat good proposals. So you can have a good proposal, but when the implementation of a Vegas sampler is weird, then it does not work out good. And knowing your problem beats everything. So with this, I thank my collaborators and I thank you for your attention.